Okay, so we will continue solving the thermodynamic relations problem, and the next problem that we are going to do is show that the specific heat at a constant volume for a van der Waals gas is a function of T only, and find the expression of it in internal energy and entropy. So, we have to show that specific heat at a constant volume for van der Waals gas. Now, the problem 4. Now, you see specific heat at a constant volume is Cv, which is del U by del T at a constant V by definition, right. So, we need to see how to do that, but there is a trick here that you need to use it. You need to use the functionality of U as an exact differential. So, meaning you need to exercise this quality of U as an exact differential, which means that you know exact differential is when d2u at dv dt is equal to d2u at dt dv. That is when the exact differential characteristics comes, which means that first you take the derivative with respect to t at a constant v, which is nothing but Cv. So, which means that del del v of Cv at a constant t is del u by del v at a constant t and derivative of that with respect to t at a constant v. So, we are going to exercise that. So, let us write that d2 u by dv dt is equal to d2 u by dt dv. Now, how did I even think of that? First of all, it will be clear why did we even think of that. So, we are writing that del del v of Cv at a constant temperature, or let us write the way we are normally writing, del Cv by del V at a constant T is equal to del del T of del U by del V at a constant T. The reason we are writing that, because are you familiar with this particular thing that we discussed during the Joule's expansion thing, that how the internal energy changes with respect to volume at a fixed temperature. So, that is the reason that we have done that. Another reason is that these variables u is a function of two variables, sorry, the thermodynamic potential u is a function of two variables, S and V or T and V and things like that. So, therefore, Cv is also function of two variables, it could be function of two variables V and T, and we need to show that it is function of one variable T. So, therefore, we need to show that if it varies with respect to V or not. If it does not vary with respect to V, then we can say it is function of T alone, because that is what we have to prove. So, if something is a function of two variable and then it does not depend on one, that means it is function of one variable only. So, that is the reason we need to do del Cv by del V T. If we show this to be 0, then we know that it does not vary with V anymore, and that is the reason we wrote del del V, and then it gives me this particular quantity del U by del V at a constant T. Another reason of writing this way, because we have shown you that this can be converted to something of P and T. For example, you know that du equal to Tds minus Pdv. Yeah, but if you do du by dv, I do not get the T here. Okay, fine, no problem, but we can write that, and then we can take the differentiation with respect to V at a constant T will give us T del S by del V at a constant T minus P. And Maxwell's relation showed us that del S by del V at a constant T is nothing but del P by del T at a constant V. So, this is the thing that we get, relation we get for this particular thing, this we have to do at a constant V. So, therefore, if I now take, okay, let us call that equation 1, let us call that equation 2, and then take derivative with respect to T on both sides, so that we get the equation 1. What we get is del del T of this particular quantity del U by del V at a constant T is, okay. So, we will not Okay, we will not do that right away, because that will be complicated. We can do a simpler approach. We can calculate what this quantity is. We can calculate what this quantity is for van der Waals gas. So, you have to say for van der Waals gas, we know that P equal to R T by V minus B minus A by V square. We discussed about that. We will just continue. Del P del T at a constant V is nothing but R by V minus B, equation 3. So, now equation from equation 2 we get del U by del V at a constant T is T del P del T V minus P, right. So, I should put that as equation 4. So, we are going to use both. So, T into del P del T at a constant V will be, as you know, that it will be R T by V minus B minus this particular quantity R T by V minus B plus A by V square, which is nothing but A by V square. So, we got that as equation 5. So, now we go back to equation 1 and we write del C V by del V at a constant T is del T of A by V square at a constant V. Since it does not depend on temperature, it will be 0. So, therefore, C V is independent of V. So, since C V comes from U and U depends on T and V, so then C V is only a function of T, at least and for van der Waals gas. So, now we have to find the expression of internal energy and entropy. Now, we will go for that this particular equation, that for internal energy and entropy we can write U as a function of V and T. Okay. So, we can write del U or du as del U by del V T dV plus del U by del T V dt. So, that means du, because we need to get the expression of U. So, we need to write du term only, and we need to write in such a way that we can get the other terms. For example, you can see here del U by del T V is nothing but C V. So, it is C V dt plus del U by del V T dV. So, del U by del V T dV, del U by del V T is we have got as this one, right, T del P del T V minus P okay. So, we got that. Now, du is, now C V depends on temperature. So, we should write C V dt plus this quantity which is T del P del T V minus P is nothing but A by V square dV. Now, integrate on both sides. Which will give you U as integration of C V T dt. So, without knowing how C V depends on T, we cannot integrate this. We have to keep it this form plus integration of A by V square dV, and so C V T dt plus, now this will give us minus 2A minus 2 plus 1 by V plus constant. So, that is how we can express U in terms of. So, we cannot do this integration because we need to know the expression of C V as a function of T. If you know that, then you can do that, because you already showed that it depends on T. If it is a constant, then C V will just come out, and typically it is assumed to be constant in cases. Then we can especially for ideal gas, you know, it is a constant, we can take it out and it will be simple T. Sorry, so it should be A by V, not minus 2, it will be minus A by V. So, if I write again C V dt minus A by V plus constant, integration constant. So, now similarly we can write S also as a function of, let us say T and V, and we can write ds as del S by, or S is a function of u and v. So, you can write as u and v as well. Okay. So, let us write that. So, del u by del v. So, del S by del u at a constant v dv plus del S by del v u at a and dv. So, now del S by del u at a constant v is nothing but p by t. You can show that. How do you show that? That you have to figure it out. And del S by del v t is no, sorry. So, this is u, right. So, this is u, I was confused. So, this is u. So, this is nothing but 1 by t, and this is p by t dv. So, you can figure it out whether it is plus p by t or not. So, you see now we got du, and du we already know as this quantity. So, 1 by t CVT dt plus a by v square dv plus p by t dv. And what is p by t? So, if we see p by t, it is p is r t by v minus b minus a by v square. So, p by t is r by v minus b minus a by t v square. So, ds is c v t by t dt plus a by v square t dv plus r by v minus b dv minus a by t v square dv, which is c v t by t dt, and this quantity cancels, giving us r by v minus b dv. Now, integrate both sides, you will get s equal to, we cannot do the integration because we do not know the form for C v, and here we can get r ln v minus b plus constant. So, that will be the expression of entropy. Okay. So, that finishes this problem. Now, we will go to the next problem. So, let us do the problem number 5. In problem number 5 is show that for a gas which obeys van der Waals equation and whose molar specific heat is a constant, volume is constant and independent of temperature, the internal energy U can be given by this. Now, we have seen that for the same system, we can write U as integration C v t dt minus A by V plus constant. So, that is the equation for van der Waals gas. We have shown that. Now, in this particular problem, it is specified that C v is independent of temperature. It can be a constant. So, we can take the C v out and we can do dt minus A by V plus constant C, which is C v t minus A by V plus constant, and that is what proves this. And this expression I am writing from the previous problem that we did. Now, it says that, and that for an adiabatic quasi-static change, show that T v minus b to the power gamma minus 1 is constant, or p plus a by v square v minus b to the power gamma is constant. That we need to show. So, now we have to show that this quantity holds, and since we are talking about this gamma Cp by Cv. So, actually this can be only done if we assume that gamma by definition is Cp minus Cv, and we have to assume that Cp minus Cv is equal to R, which is only true for ideal gas, but we have to assume that for van der Waals gas also, taking into account that it is a very dilute gas. So, if you do that, then again we can write the expression of S ds as 1 by T du plus P by T dV. Now, 1 by T du we already know what it is, or we already got that expression of that. We can write this one as you can see as ds. So, Cv by T dt plus R by V minus B dV. So, Cv by T dt plus R by V minus B dV. Okay. So, this we already got without any approximation for van der Waals gas. Now, in order to introduce the gamma, and we know that for adiabatic reversible adiabatic process ds equal to 0. So, 0 equal to Cv by T dt plus R by V minus B dV. Okay. So, now we can write Cv dt by T is minus R by V minus B dV. Now, you see that we can write R for an ideal gas as Cp minus Cv. And that is not true for van der Waals gas, but we are assuming that because otherwise we will not get the gamma. So, dt by T equal to minus, now we divide by Cv. So, we will get gamma minus 1 by V minus B dV. Okay. So, now once you get that, you see we can get integrate on both sides, and we can get ln T equal to minus gamma minus 1 or 1 minus gamma you could have done ln V minus B plus constant. So, ln T is minus ln V minus B to the power gamma minus 1 plus constant as C. So, now you can see I can bring it the left hand side ln V minus B to the power gamma minus 1 is equal to C, or ln T into V minus B to the power gamma minus 1 is equal to C, or T into V minus B to the power gamma minus 1 is e to the power C, or let us say another constant C prime. So, we can see that T into V minus B to the power gamma minus 1 is a constant for quasi static reversible adiabatic changes. We just took ds equal to 0 and we just took R to be Cp minus Cv approximately. So, that is like an approximate changes that we have done here, approximation. That is why we got the gamma. Okay. So, this we have shown, and now and that is same as showing that you can show the last part, same as showing that it is P by A by V square V minus B to the power gamma. You know that P equal to R T by V minus B plus A by V square minus A by V square. So, P plus A by V square into V minus B is R T, that you know. Therefore, we can write the same equation 1 as, so just replace the T by P plus A by V square V minus B by R into V minus B to the power gamma minus 1 is a constant, and then we can write P plus A by V square V minus B, and V minus B gamma to the power 1 is V minus B to the power gamma is equal to R into constant, which is another constant, that is also proved. Okay, so, that brings us to all the tutorial problems that we have decided for the thermodynamic relations, and also that brings us to the end of all the lectures of these chemical principles too. So, I would like to mention to you is that we have used first law of thermodynamics, second law of thermodynamics from classical approaches, second law of thermodynamics from statistical approaches, and then we have used the fundamental equations of thermodynamics and derived all the thermodynamic relations, Maxwell's relations and everything. We have talked about heat engines, their efficiencies, and also you have showed that different principles, different statements of second law, for example, efficiency cannot be 1 is in turn related to the efficiency, the entropy of the universe is increasing. and entropy from the statistical point of view means nothing but the possibilities. So, I hope that you will be able to apply these principles in different situations in both experimental when we are observing, when you are observing something, or when you are doing some experiments, or any other situations in day to day life. You will be able to associate the changes from the fact that the entropy of the universe is changing, or if you only look at the object that you are looking at there, you can find out whether the free energy, Helmholtz free energy or Gibbs free energy or other quantities are changing or not. So, in short, that any change that we observe that will be governed by these principles of thermodynamics. So, I hope that you will get benefited from this course, and it will be helpful in whatever you want to apply it for or learn it for. Okay. Thank you.